Welcome back to the lecture series Logic Design CMP223. In the previous class, we were able to look at the Boolean identities, some of their provings using the truth table. You were also introduced to SOP, sum of product form, and also product of sum form. And then we are also able to look at the standard forms of SOP and POS, right? So in today's class, we are going to continue our discussion by looking at the other simplification techniques. So you will be introduced to simplification using K-map. So the Karnoff map, which is often abbreviated as K-map, is a graphical representation and a tool, used in digital electronics and Boolean algebra to simplify Boolean expressions and also optimize logic circuits. So it is especially useful for simplifying complex logic functions with multiple variables. The K-map technique actually uses the Greek code ordering for the input variables. So one of the application of Greek code is in the use of K-map to simplify Boolean expressions. So it actually arranges the binary values so that only one bit changes between adjacent cells. This actually helps in identifying adjacent ones more easily. So it is worth taking note of that in filling the cells of the uh, K-map cells or K-map table, uh, the values we use is gray code ordering and not binary. Let's quickly see how that actually works. Consider a two variable truth table. So let's assume a two variable truth table giving thus. So let's assume two variables in terms of A, B, and then let's populate them as usual with a number of zeros and one. So if we do that, let's assume this is going to be a 1, 2, 0, sorry, 1, 2, and then 3. So this is 0, 0, 1, 1. And then this is 0, 1, 0, 1, right? So now if you look at it, this is binary number 0 in the first instance. This is binary 1. This is binary 2. This is binary 3. So what we're trying to explain is the ordering of the K-map does it follows the gray code and not binary, right? The reason is because if we were to continue with this number of variables in terms of, let's say, three variables or four variables, you will see that with binary coding system, more than one bit will be changing. But with gray code, it has this uniqueness whereby the change happens just a single bit, right? So for instance, in generating the first three digits of gray code can be explained as follows. For instance, let's generate the first three digits of gray code. So the first uh, bits combination of gray code, first digit of gray code can be given as what? Zeros and one using a technique that we refer to as reflected mirror. So from this, if I want to get or generate the 2-bit gray code, right? So this is 1-bit gray code. So for the 2-bit gray code, this can be generated having known the first bit gray code. So all you need to do So you have this, and then you take a mirror, right? So for this, you have 0. So between the demarcation, the first one, you fill it with all zeros, right? Fill it with all zeros, and then the next one, you have all ones. So similarly, if I want to get a 3-bit gray code, right? So I will use the preceding one, the 2-bit gray code, and then take a reflected mirror. So by this, I will have what? I will have 0, 0, 0, 1. I have 1, 1. Then I have what? 1, 0. I will now take a mirror. I'll start 1, 0, 1, 1, 0, 1, and then 0, 0. So in between the demarcation, I will start with zeros all through, and then I'll fill these ones with what? With 1. So you can do that for the 4-bit gray code, 5-bit gray code, depending on the number of variables you are looking at. So this is just a simple demonstration on the uniqueness of gray code with its application in KMAP, right? So let's brush up. Let's look at some of the rules that has to do with KMAP or simplification using KMAP. What are the rules guiding simplification? Is using KMAP. So the groups can only contains one. So it's a situation whereby if you are looking at mean terms, right? So if you are dealing with mean terms, as far as the Boolean expressions is concerned, so the groups can only contain ones and not zeros. So only ones in adjacent cells can be grouped, right? So diagonal grouping is not allowed, right? So what we mean by this, for instance, when you have consider the following table, assuming we have these cells of KMAP, right? So there are certain way you group the KMAP, and there are certain ways you are not supposed to actually group them. So what we mean by the diagonal grouping is not allowed is let's assume we have this. Let's assume we have this. We have this cell fill up with 1. So by diagonal, so the grouping like this is not allowed in KMAP, right? So let's also have this. So assuming we have these cells, so let's make it a 4 variable. So we can show to you how adjacent cells can be grouped. So let's assume we have 1 at this instance. We have 1 this way, and we have 1 this way. We have 1 this way. So this, in an attempt to look at the largest possible group of 1, so this can be grouped, right? So let's look at the other rules. So only ones in adjacent cells can be grouped. Diagonal grouping is not allowed, just like we've seen. The number of ones in a group must be what? Power of 2. Remember what we mean by this power of 2? So the powers of 2 can take in the form of can take the form of 2 raised power of 0, 2 raised power of 1, 2 raised power of 2, 2 raised power of 3, up to what? 2 raised power of n. So where your n can take in the form of 0, 1, 2, 3, etc. Right? And then, excuse me, the groups must be as large as possible while still following all rules. And then all ones must belong to a group, even if it is a group of what? One. Now, overlapping groups are allowed. Also, wrap around is also allowed. And then you try as much as possible to use fewest or uh, less number of groups possible, right? So with following by following all these rules, you should be able to minimize your Boolean expressions using the KMAF technique, right? So let's quickly see an example using the KMAP method. So assuming we are given the expression, let's copy that. Assuming we are to simplify this expression, f is equals to xy plus x into bracket y plus z plus y into bracket y plus z. So given that, for us to simplify, you know, using the Boolean, using the kind of map, using the kind of map. So what we need to do, first you need to identify the number of variables, right? So before we solve this problem using Kanoff map, so let's try to draw a three variable K map and maybe a four variable K map. So this is how a three variable K map actually looks like, right? Drawing a three variable K map. So in this case, our three variables are what? The X, Y, and what? And Z. X, Y, and Z. So X, Y, and Z. So in filling that, remember we said it's gray code. So you have the 0, 0 in the first column. Then in the second column, you have your 0, 1. In the third column, you have what? 1, 1. Then the last column, you have what? 1, 0. So preceding that is 0, then 1, right? So what we are trying to say, so we can populate this by saying this word at this cell. We are dealing with what? X bar, Y bar, and what? Z bar. In this second cell, we are dealing with what? X bar, Y bar, and what? Z. In the third cell, we are dealing with what? We are dealing with X bar, Y, Z. In the last cell, we are dealing with what? X bar, Y, Z what? Z bar. Similarly, in this cell, we are looking at X, Y bar, Z bar. Similarly, in this cell, we are looking at what? X, Y bar, Z. In this cell, we are looking at X, Y, Z, right? In the last cell of the second row, we are looking at X, Y, what? Z bar. So this is necessary because if you are dealing with min terms, Zero appears complemented, and then ones appear what? Uncomplemented, right? So let's have this. Going back to the expressions, right? Uh, so first thing, what you need to do, you need to rearrange this and factor out the terms, and then you standardize it, and then try to put it in order to have to clearly represent it in the cell of the Canop map, right? So going back to our expressions, we have that what? Xy plus. So let's open the bracket. You have what? Xy plus what? Xz. And then you have what? Y multiplying by y plus what? Y is multiplying by z. Now, if you look at or examine the new expression, you see certain terms are repeating, like xy repeating in two places, and then you have y dot y. So, excuse me, from one of the Boolean identities, we're meant to understand that what? That x plus what? Plus x, sorry, x plus x, as far as the Boolean mathematics is concerned, this is can be resolved to be x. Similarly, you have when you have x dot x, this can be equivalent to what? To what? To x. Excuse me. So in applying that to your expressions, right? So we'll go with one of the x. So you have xy plus what? Xz plus what? Plus y plus y what? Excuse me. Yz, right? Now, we've already established that active variables as far as this expression is concerned. In the first instance, in the first term, z is missing, right? So in standardizing that, we are going to introduce the missing variable. So in this case, is what? Z, right? So if you do that, we are going to have x, y, z plus what? X, y, z bar. You can refer to our first one of our classes on what? On the standard forms of SOP, right? Then in the second part, which is xz, so we're introducing y, right? So in this case, we are going to have, excuse me, we're going to have what? X, y, z plus x, y bar, and then z. The next term is y. Two of those variables are missing. Two of those variables are missing. So let's see how we can introduce the missing variables in terms of x and what? X and z. So if we do that, let's just write that here quickly. So the next time we are considering is y. So we are looking at y. So if you introduce the missing variables in terms of y, this is going to be x, excuse me, xy plus what? X bar y, right? That should be the first instance. And then these two terms, we are still going to introduce the value for z. So in the first part, this will lead to what? X, y, z plus what? X, y, Z bar, right? And then this will also lead to what? X bar, Y, Z plus what? X bar, Y, Z bar. So these are the terms, four terms that was given birth by Y. So in writing that, we're going to have what? We're going to have plus X, Y, Z plus what? X, Y, Z bar plus what? X bar, Y, Z plus what? X bar, Y, Z bar. Right? So again, if you look at the last expression, you will notice that some of those terms are repeating. For instance, XYZ appears here. We have another one here, XYZ, another XYZ3 here, right? So in three places. So XYZ bar, let's see, XYZ bar, SYZ bar appears one here, SYZ bar appears, we have a second one here. And then let's see, XY bar is unique. S bar YZ, S bar YZ is also unique, right? So this time, so let's see, it's also unique. So let's have some space. So let me clean this table so that we can have the final expressions. So let's see if you go with that. So we are going to have this is equal to. So let's take those ones that are unique without repeating some of those expressions that appears more than one. So we have x, y, z, right? X, y, z bar appears twice too. So we pick just one. X, y, z bar, right? Z bar, and then plus um x, y bar, z, right? Plus x bar, y, yz, plus x bar, y, z bar. So the terms have been reduced to 1, 2, 3, 4, 5 out of 1, 2, 3, 4, 5, 6, 7, 8, right? So we've reduced those terms where, so as it is now, we can comfortably, uh, put this in our K-map and then simplify that, right? So let's see, let's do away with this. Let's do away with this. So remember, we are dealing with it, a three variable K-map, right? In terms of X, Y, and Z that we drew earlier. So let's draw that and populate that. Right? So the three variables in terms of x, y, z. So remember we drew this earlier. We have 0, 0, 1, 1, 1, then 1, 0, 1, 0. So this is going to be 0 and then 1. Then we said this is our x bar, y bar, then z bar, right? So this is our x bar, y bar, and then z. This is our x bar, y, z. This is our x bar, y, z bar, right? So in the second rule, we have this is x, y bar, and then z what? Z bar, right? In the second column of the second row, we have this is our x, y bar, and then z. In the second column of the second row, you have x, y, and then z. In the last part, you have x, y, then z what? Z bar. So these are all the possible combinations as far as the three variable K-map is concerned. So we need to identify the positions for x, y. This is where our position we are going to put our one based on the given expressions, the Boolean expression. So let's see x, y, z. X, y, z is that's where our one is going to be. So we are having our one here. X, y, z bar, x, y, x, y, z bar. At this position, one, right? At this position, one. And then, so we've taken care of this. We've taken care of this. X, y bar, z. X, y bar, z. We have this. And then we've taken care of this. X bar, y, z. X bar, y, z. Here, position of 1. This. So the last one, x bar, y, z bar. X bar, y, z bar, which is this, right? So in following the K-map rules, we are grouping the ones in terms of powers of 2 and then try as much as possible to pick the highest powers of 2 while as well maintaining the less group, right? So looking at this, our first grouping will be this, right? Which is the largest possible, the largest powers, the largest group we can see, right? So we can call this 1. And then for this, we can pick this to be our second group, right? So we can call this what? 2, right? So we can call this group 2, right? So from 1, so what we'll do now, we'll try to check across the group 1, excuse me, across the group 1. You check among the variables what is changing and what is not changing. So starting with the variable x, so x bar, so x bar has changed um, in the third column, the third row. So it has changed from X bar to X as far as the group one is concerned. So you discard that. So any of the variable that is changing, either from 0 to 1 or 1 to 0, you discard that. So let's check Y. So you can see in group one, Y again. So Y remain constant. So you keep Y. You go to the next variable, which is Z. So Z has changed from Z to Z, right? So similarly, we can say from 2, that is the group 2 now. We see that when we compare this, you check X remain constant. So there's no change. So you keep X. Y bar has changed to Y, and then Z remain constant, so you have Z. So our final expressions now will be if you add the 1 and 2, so it's going to be this is equal to you have X Z plus what? Plus Y to be our simplified expression, right? So this is how you go about simplifying or simplification using K-map, excuse me. So you can look at the other exercise. You can look at the other examples. I can take them as exercise. Try to simplify them using K-map. So in the next class, we are going to be looking at the other simplification techniques. So we'll be introducing you to the Queen MC-Kloski minimization technique, which is also referred to as the tabular method. So see you in the next class. Thank you.